Here is a quick introduction to the technique of batch normalization. You might remember that we mentioned that we could not directly change the shape of the error surface. If the error surface is very rugged, it is harder to train. Then can we level the surface directly to make it better to train? Batch normalization is one of the ideas of leveling the surface. When we talk about optimization, I said that not to underestimate the problem of optimization. In the beginning, sometimes even if your error surface is convex, or it is the shape of a bowl, it is not necessarily easy to train. For example, suppose the slopes to loss of the two parameters are very different. The slope changes slightly in the direction of W1. The slope changes greatly in the direction of W2. If you use a fixed learning rate, you may have a hard time getting good results. That's why we said that you need an adaptive learning rate. You need to use advanced optimization methods, such as ATOM, to get good results. Now let's look from another perspective, which is changing the rugged error surface directly. Can we get good results? The first question we have to ask is, what made the slopes of W1 and W2 differ so much? Where did it come from? Let's look at an example here. Suppose we have a very simple model. The input of the model is x1 and x2. The corresponding parameters of x1 and x2 are w1 and w2. It is a linear model with no activation function. Y equals to w1 times x1 add w2 times x2 add b. The difference between y and y hat is e. The loss is the sum of all e. In training data, then you want to minimize your loss. What kind of situation will result in the hard-to-train error surface mentioned above? Let's take a look at this W1. How do we analyze the loss? When there is a change in W1, when we made a small change to W1. For example, when a delta W1 is added, then the L will also have a change. What about the W1? When you change W1, you also change Y. And when you change Y, you also change E. Then L is changed. So when W1 changes, L changes accordingly. When will the change of W1 have little effect on L? When does the change of W1 have a little slope of the error surface? One possibility is when your input is small. Suppose the values of x1 are very small. Assuming that the values of x1 are small in different training examples, and because x1 is directly multiplied by W1, if the values of x1 are very small, when there is a change in W1, the impact on Y will be small. The impact on E will be also small. The impact on L will be also small. So, if the input numbers which will be multiplied by W1 are relatively small, then changes in W1 will have a small influence on L. On the other hand, if the values of x2 in the input data are all relatively large, then small variations of W2 may still have a large influence on Y, because the variation of W2 will be multiplied by x2, which has a large value. A great change in Y produces a great change in E, and a great change in L. So the error surface is steep in the direction of W2 compared to other directions. Let's conclude the discussion. We discovered that if the magnitude of some dimensions values are large, while the values are small for other dimensions, then the error surface has a bad behavior, in the sense that the magnitude of the slope varies a lot between different directions. How can we deal with this problem? Is it possible for us to modify the feature vectors such that every dimension's values lie in the same range? If we do this correctly, we may be able to create a better error surface to make training easier. But how can we squeeze every dimension into the same range? Actually, there are many different ways to do this. Usually, we call all those methods feature normalization. The method I'm going to talk about is only one plausible way of feature normalization. It is not the entirety of feature normalization. Let's start. Let's call the feature vectors in the training data x1, x2, etc. Also, label the elements in a vector with upper indices. For example, x superscript 1 subscript 1 stands for the first element, of the first vector. X superscript 2 subscript 1 stands for the second element of the first vector, etc. For the first dimension, collect every feature vector's first element and calculate its mean. Do the same for every dimension. The notation mi stands for the mean of the ith dimension. Also, calculate the standard deviation of every dimension and represent the mth dimension's standard deviation as sigma I. Now let's normalize all the dimensions. Actually, the normalization we are going to do has another name, standardization, but I will call it normalization in the rest of this class. So how do we do normalization? We subtract the mean of this dimension from the x shown here, which is one of the values. We then take the subtracted x and divide it by the standard deviation of this dimension. We get a new value called x tilde by subtracting the mean from x and divide it by the standard deviation. We then replace the old value with the new value. From now on, I will use the tilde symbol to represent the normalized value. Now, what are the benefits of normalization? After normalization, the mean of this dimension will be 0. And the variance will be 1. So, this row of values will be distributed around 0. Now, we apply normalization to every dimension. This way, every dimension will have its mean close to 0, and its variance close to 1. We can see that the values of every feature across different dimensions all lie around 0. This may, in turn, create a better error surface. This is why doing feature normalization is often helpful to the training process. It makes the loss converges a bit faster. When doing gradient descent in the training process, this should make gradient descent a bit smoother during training. All in all, that's feature normalization. Of course, feature normalization can also be applied to deep learning. In fact, in the sample code provided by the teaching assistants, feature normalization is always used. After we get x tilde, which is the normalized feature, we use it as the input of the deep network to do further calculations and conduct the training process. We pass x1 tilde through the first layer to get z1. We then pass it through an activation function, whether it's sigmoid or ReLU, to get a1. And so on, depending on how many layers of network there are. We do the same process for every x. But if we think about it, for W2, A1 to A3 and Z1 to Z3 can be considered as another kind of input. However, even if x tilde is normalized, it's no longer normalized after being passed through W2. If we get Z1 by passing x tilde through W1, and there is still a big difference in the distribution between different dimensions of Z1, will we face difficulties training the parameters of the second layer? Come to think of it, we should also apply feature normalization to A and Z. For W1, A and Z are also features, and we should normalize these features. You might be unsure whether you should do normalization before the activation function or do normalization after the activation function. In practice, they're pretty much the same. If you try it yourself in the homework, you can see that these two implementation methods aren't too different in reality. So, whether you do feature normalization for Z or do feature normalization for A are all fine. If you choose sigmoid, doing feature normalization for Z is much recommended. You know that sigmoid is an S shape, so it has a larger slope near 0. If you do feature normalization for Z, which will move all the values neighboring 0, when you are counting the gradient, the calculated value will be larger. Since you may not use sigmoid, it is not necessary to do feature normalization for Z. If you choose something else, perhaps you choose A, it may have a better result. Maybe. In short, generally speaking, this normalization could be put before or after the activation function. Practically, there may not be much difference. Okay, here, we do it on Z. We do feature normalization on Z. Okay, how do we do feature normalization on Z? Then, you consider Z as another feature. Here, we have Z1, Z2 and Z3. We take z1, z2 and z3 out. And we calculate its min. How do we calculate its min? The mu here is a vector. We calculated the mean of these three vectors, z1, z2 and z3. To get this vector, mu. Then, we can also calculate a standard deviation. This standard deviation here contains a sigma, which also represents a vector. How does this vector be calculated? You just subtract mu from zi. And then square it. The square is here. The notation here is a little bit confusing. The square here means to square every element and apply the root sign. The root sign here should be applied to every element in a vector. We apply the root sign on every element to get sigma. Anyway, you know what I mean. For these three vectors, we just calculate every dimension inside to get their mu and their sigma. Okay, here, I won't draw those arrows. From z1, z2 and z3 to mu and sigma. Next, you let every z here be subtracted by mu and be divided by sigma. You subtract mu from zi and divide it by sigma. You would get the zi tilde. The mu and sigma here are all vectors. So, the notation of this division here is a bit of abuse. What I mean here is element-wise division. That is, zi minus mu is a vector. The numerator is a vector. And the denominator is a vector, too. Dividing the value of the corresponding element in these two vectors is what the division sign here means. We get z tilde here. Okay, so we just subtract mu from z1 and divide by sigma to get z1 tilde. Similarly, z2 minus mu divide by sigma to get z2 tilde. z3 minus mu divided by sigma to get z3 tilde. That is, we perform feature normalization on z1, z2, and z3 to get z1 tilde, z2 tilde, and z3 tilde. Okay. What should we do next? You can do what you want, like get other vectors through activation functions, then pass them through other layers, and so on. That's it. So, you perform feature normalization on z1, z2, and z3 to get z1 tilde, z2 tilde, and z3 tilde. There is an interesting thing here. The mu, sigma here are actually calculated based on z1, z2, and z3. So, the z1 here, if we originally didn't do feature normalization, changing the value of z1 will change the value of a here. But now, when you change the value of z1, mu and sigma will also change accordingly. After mu and sigma change, the value of z2, the value of a2, the value of z3, and the value of a3 will also change. Originally, x1 tilde, x2 tilde, and x3 tilde were handled separately. But after we do feature normalization, these three examples become related to each other. As long as there is a change on z1, z2, a2, z3, and a3 will also change. Thus, you should, when feature normalization is applied, you have to take this whole process, which collects a bunch of features, and calculates this bunch of features into mu and sigma, as part of the network. In other words, now you have a relatively large network. Your previous network only needs one input, and it has one output. Now, you have a large network. This network eats a bunch of input, and uses them to calculate mu and sigma, then generate a bunch of output. This part is a bit abstract. I don't know if you guys have it. I hope you understand. If you feel confused, you can ask later, or ask on the discussion board. In this section, I think it can only be understood like this. I don't know whether you can understand this section. It's not the situation that one network handles one example, but there is a huge network handling a bunch of examples. Use a bunch of examples to calculate mu and sigma, and then get an output. There will be a problem. In your training data, you have a lot of data. There are millions of pieces of data in a benchmark corpus. How can you put millions of data into a network at once? The memory of your GPU can't handle it. This one is dead. The microphone is dead. Great. Okay, your GPU memory cannot load the data of the entire dataset. So, what to do? During implementation, you won't let this network consider all examples in the entire training data. You will only consider examples in a batch. For example, the batch size is set to 64. Your huge network just reads 64 pieces of data and calculate the mu of these 64 pieces of data and calculate the sigma of these 64 pieces of data and then perform normalization on all 64 pieces of data. Because during the implementation, we only deal with the data in a single batch to do normalization, so this trick is called batch normalization. This is the batch normalization you often heard of. Obviously, there is a problem with batch normalization. You must have a large enough batch to calculate mu and sigma. Suppose today you set your batch size to 1. Then you don't have any mu or sigma to calculate. You will have problems. So, batch normalization is suitable when the batch size is relatively large. If the batch size is larger, maybe the data in this batch size is enough to indicate the entire corpus's distribution. If so, you can change the object, which should be performed feature normalization, from the entire corpus to a batch of examples, as an approximation. When doing batch normalization, there are often such designs. After you calculate this z tilde, next, you will put this z tilde multiplied by another vector called gamma. This gamma is also a vector. So you take z tilde to do element-wise multiplication with gamma. Take the element in the z vector and the element in the gamma vector to do element-wise multiplication. We add the beta vector to the multiplication result and get z hat. For beta and gamma, you have to think of them as network parameters. They can be learned by updating the network. Then why do we introduce beta and gamma? Some people might think, after we do normalization, the average of z tilde must be 0. However, if the average must be 0, it can be seen as a restriction to the network, and this restriction may bring some negative effects. We add beta and gamma back, so the average of its hidden layers output will not be restricted to 0. If the network wants the average to be non-zero, the network will learn beta and gamma by itself to adjust the output distribution or the distribution of this z hat. But someone will ask, you said that to make the range of each dimension the same, we have come up with the solution of batch normalization. But now, if we multiply it by gamma and add beta, does this operation make the distribution of each dimension different again? It is possible. But in practice or during training, when it comes to the initial values of gamma and beta, you will set the initial value of gamma to 1. So initially, gamma is a vector that contains only ones, and initially, beta is a vector that contains only zeros. So gamma is one vector that contains only 1. Beta is a 0 vector that contains only 0. So in the initial stage of the network training, the distribution of each dimension is relatively close. Maybe after training for a long enough time, we have found a better error surface or reach a better place. Then the training will add gamma and beta slowly. Okay, so adding batch normalization is often helpful for your training. Okay, then I'm going to talk about the testing part. What I just talked about is the training part, and I haven't talked about the testing part yet. The term testing is sometimes called inference. So in some papers, when the author mentions the term inference, it refers to testing. Batch normalization will cause problems during testing or inference. What kind of problems? While testing. If you are doing homework, we will give you all the test data at once, so you can actually make batches from the test data. But if you have a system online, a real online application, can you wait for 64 pieces of information to come in, assuming your batch size is 64, then doing the calculations once? This is obviously not feasible. If this is an online service, you have to do the calculations every time data comes in. You can't do the calculations after accumulating a batch of data. However, when we do batch normalization, x tilde, a normalized feature comes in. You get a z. Then subtract mu and divide sigma. The mu and sigma are calculated using a batch of data. But when testing, there is no batch at all. Then how do we calculate this mu? How to calculate this sigma? The solution, in practice, looks like this. If you use PyTorch, you don't need to do anything special. On batch normalization during testing, PyTorch will take care of it. How does PyTorch handle this? During training, if you are doing batch normalization, during training, it will calculate the moving average of mu and sigma calculated in each batch. What does that mean? Every time you take a batch out, you will calculate mu1. When you take the second batch out, you calculate mu2. When you take the tth batch out, you calculate mu-t. Then, you will calculate a moving average. That is, you will multiply the average value of mu you calculated, called mu bar, with a factor. This is also a constant. This is also a constant. This is also a hyperparameter. It needs to be adjusted. In PyTorch, p is 0.1. If memory serves me right. Okay. Then we add 1 minus p, multiplied by mu-t. Then update your average value of mu. Finally, in testing, you don't need to calculate mu and sigma in batch. Because when testing, on the real application, there is no such thing as a batch. You just use mu bar and sigma bar directly. That is, we replace mu and sigma with the moving average of mu and sigma during training, which is mu bar and sigma bar. This is how batch normalization works during testing. Okay, this is an experiment result, extracted from the original paper of batch normalization. There are many other things mentioned in the original paper. For example, what we haven't talked about is how batch normalization is used on CNN. How to use it. After reading the original paper, you will know that, if you want to apply batch normalization on CNN, how it should be done. Okay, this is a result extracted from the original paper. This horizontal axis represents the training steps. This vertical axis represents the accuracy on the validation set. The black dashed line is the result without using batch normalization. It uses the network called inception. It's a certain kind of network architecture. It is also a network architecture based on CNN. Anyway, the black dashed line represents the result without using batch normalization. Then if batch normalization is used, you will get this red dashed line. You will find that the training speed of the red dashed line is much faster than the black dashed line, although the final results, when they are converged, which take enough training time, may all reach the same accuracy. But the red dashed line can achieve the same accuracy in a relatively short period of time. These blue diamonds over here indicate that the accuracies of these points are the same. The red dashed line takes only half of the time. Compared to that without using batch normalization, it only takes half, or even less time, to achieve the same accuracy. There are other lines here. There is a pink line here. What is this pink line? The pink line is the result using the sigmoid function. As for the general concept of the sigmoid function, although we haven't discussed this matter yet, generally, we choose ReLU instead of using sigmoid function, because using sigmoid function will make the training much difficult. But I want to emphasize here is that even using sigmoid makes the training much difficult. After using batch normalization, we could still get an acceptable result. Note that there is not a result that uses sigmoid, while without using batch normalization, because in this paper, the author says that the experiment using sigmoid without batch normalization can't even train at all. Okay, there is a blue solid line. What about the blue solid line and the blue dotted line? They are trained with some larger learning rates. Cross 5 means that the learning rate increases to 5 times. And cross 30 means that the learning rate increases to 30 times. That's because if you apply batch normalization, your error surface will be smoother and the model will become easier to train. Applying batch normalization makes your error surface smoother, so you can larger your learning rate. There's a strange thing here that is hard to explain. For some reason, when the learning rate is 30 times the original, It's worse than when it's 5 times. The author didn't give an explanation. As you know, sometimes this kind of weird, unexplainable thing happens when you're doing deep learning. The author just truthfully presented the results of his experiments on this graph. Okay, the next question is about batch normalization. Why is it helpful? In the original paper discussing batch normalization, he came up with a concept called internal covariate shift. The term covariate shift already exists, but internal covariate shift, I think, is invented by the author of the paper. He believed that when one trains a network, the following question will occur. The question is like this. A network has many layers. After X goes through the first layer, we get A. After A goes through the second layer, we get B. After we calculate the gradient, we update A to A prime and B to B prime. But the author thinks that when we update B to B prime, when we were calculating the gradient, to update B to B prime, the parameters of the previous layer were A. Or in other terms, the output of the previous layer was A. When the previous layer changes from A to A prime, its output changes from A to A prime. But when we calculate this gradient, we calculate it based on this A. So maybe the direction of this update is suitable for use on A, but not suitable on A prime. So if we do batch normalization, we will let, because we do normalization every time, we will let A and A prime have similar distributions. Maybe this will be helpful for training. But there is a paper called How Does Batch Normalization Help Optimization? Which gives a slap in the face to this internal covariate shift concept. In this paper, he tells you from all aspects that internal covariate shift, first of all, is not necessarily a problem when training a network. Secondly, the fact that batch normalization is better may not be due to its ability to solve internal covariate shift. In this paper, he did a lot of experiments. For example, he studied the distribution of A during training and found out that the distribution hadn't changed much, whether you had done batch normalization or not. Then, he said, even if it changed a lot, it didn't do much harm to the training process. He also said that no matter if the gradient is calculated based on A or A prime, the directions were almost the same. So it tells you that the internal covariate shift may not be the training network. The main problem is that it may also not be the key to a good batch normalization. For more experiments, you can refer to this article by yourself. Good. So, why is batch normalization better? This paper, How Does Batch Normalization Help Optimization, experimentally and theoretically, supports that batch normalization can change the error surface. It makes the error surface less rugged. So this view is supported by not only theory, but also experimental evidence. In this article, the author also says a very interesting thing. He says he thinks that it's a positive impact on batch normalization, because he says that if we want to make networks error surface become less rugged, it's not necessary to do batch normalization. There are many other ways that can make the error surface less rugged. Then he tried some other methods and discovered that they perform similarly to batch normalization, even slightly better. So he said the following exclamation. He thinks that the positive impact of batch norm on training may be somewhat serendipitous. What is serendipitous? This word may be translated as accidental, but accidental did not fully express the meaning of this word. This word means that you found something unexpected. For example, penicillin is an unexpected discovery. Everyone knows the origin of penicillin. There was a man named Fleming. He originally wanted to cultivate some staphylococci, but because he didn't do the experiment well, his staphylococcus was infected. Some mold fell into his petri dishes. And then he found those molds in his petri dishes would kill staphylococci, so he invented penicillin. This is an accidental discovery. The author of this article also thinks that batch normalization is also like penicillin, which is an accidental discovery. But anyway, it is a useful method. Okay, Actually, batch normalization is not the only way of normalization. There is a lot of normalization methods. There are a few well-known ones listed here.